Okay, I just want to relate what we've been talking about with Stokes' theorem to something that we talked about earlier in this chapter, which is conservative vector fields. So if f is a conservative vector field in 3 space, remember that just means that f is the gradient of some potential function. Okay. Now, if S is a surface and C is its boundary curve, that tells me that C must be a closed curve. And for Stokes' theorem, we were requiring that it was sufficiently nice, so it has to be piecewise smooth. Okay. But we had learned that the integral of a conservative vector field around any closed curve would have to equal 0. Remember, they're independent of path along any path, but if it's a closed path that returns to its starting point, the work integral is just going to give us 0. Well, we also learned that if f is conservative, the test for that in 3 space is whether on a simply connected region, the curl of f is equal to 0. Well, if it's conservative, and I apply Stokes' theorem to get the double integral over s of the curl of f dotted with n d big S, that would be the double integral over s of 0 dotted with n ds, which would be 0. So the pieces do come together very, very nicely. If it's conservative, I can get that work integral around a closed curve is going to be 0 one of 2 ways. I can use that fact from conservative vector fields that we studied back in, I think, 16.3, or I could use the fact that if it's conservative, its curl is 0. So if I apply Stokes' theorem to do a surface integral, I'm just going to be integrating 0, and I'm going to get 0.